This is section 11.1, the law of sines. Okay. In geometry in high school, I assume you talked about congruence of triangles, and you could prove congruence with one of several things. You could say this one is congruent to another one if you know a side, an angle adjacent to that side, and then another side in that order. So in other words, the angle has to be between the two sides that you know. And if you could show that those two sides were congruent to another triangle's two sides. Hold on, I need to fix something because my mark didn't look very good. There we go. I'll make this 2 marks. Side 1 is congruent to side 1 of another triangle. Side 2 is congruent to side 2 of the other triangle, and the angle between them, that those are congruent. It's called side angle side. Another way to prove that two triangles is congruent is angle side angle. So angle side angle. And then the third way is side side side. So the congruence of, or 3 sides that are all the same length as 3 sides of another triangle are congruent triangles, so side side side. Okay, so if we're going to solve triangles, we know that if it's a right triangle, we have all kinds of information that we've been using. The sum of the angles, is 180 degrees. Okay. Wait, I should have, wow. I'm seeing I should have done this a little bit differently. I'm going to change that title. So, I meant to say right, I think I said right triangles, but I didn't write right triangles. So, I really wanted to say that. So, pardon me for backing up here and changing what I'd written earlier. So for solving right triangles, we have several things that we can use. Because remember, when we solve a triangle, we end up knowing all 3 angles and all 3 sides. So if you're given 2 angles, you can find the third angle by subtracting both of them from 180. We also know the trig relationships for a right triangle. We know that the sine of an angle is opposite over hypotenuse. We know that the cosine of an angle in a triangle is, right triangle is adjacent over hypotenuse. Remember, this is all right triangle stuff. And tangent of theta is opposite over adjacent. And then there's one other thing we know about right triangles is that if it's triangle ABC and C is a right angle, is our right angle in that, then we know that A squared plus B squared, leg squared plus leg squared, equals the square of the hypotenuse. And those are all right triangle things that we can rely on. Now, if a triangle is not a right triangle, it's called an oblique triangle. And very little from that list over to the left actually pertains to this over here, because most of that is only true for right triangles. The only thing I'm going to be able to pull over from there is that the sum of the three angles is still 180 degrees. Oh, and by the way, since we're solving triangles, we're back to, in this part of the chapter, we're talking about triangles. All of our angles will be measured in degrees, not radians for this. Okay, that's it. Because the trig relationships and the Pythagorean theorem only apply to right triangles. So that's a very short list, and we're going to need to know more stuff to be able to solve oblique triangles. So we're going to have to introduce some new material. Okay. There are several cases that we will encounter when it's oblique. We might be given a side angle angle, or angle side angle. That's case one. And that one's actually, to get started, you'll know two of the angles already. And finding the third angle is easy. You can use what I've already written up above. But to find the other sides, you're going to have to know something else. Okay? So that's one of the types of problems we'll encounter. Two sides and one angle that's not between them. In other words, side-side angle. And this one is probably the hardest one because you can have no triangle that actually exists that has that information that's given to you. There could be one right triangle that actually exists for the given information. Or there could be two oblique triangles that exist given that information. And because of this ambiguity as to, will I have no triangles, one right triangle or two oblique triangles, we always talk about this case as the ambiguous case. When I taught in high school and I wanted to talk about side-side angle, my sophomores and juniors in the class could often be kind of silly, rather sophomoric, and they would like to say it the other way around and call it the ASS triangle, and then say, ah, it's ass, and then giggle, you know, immature kids, you know how that is. Actually, though, that is a pretty good reminder that this is the tough one, that it's ambiguous, because this is a problem that you could feel like it's making an ass out of you because you're having to do so much work to figure out, first of all, which of those three situations it is, and then if there is a triangle or two, you have to solve them, of course. So this is the toughest one, and we will get back to that pretty soon, but that is one of the most challenging of the four cases that we're going to encounter here. Okay, the third case is if you're given side angle side, and the fourth case is when you're given side side side. And depending on which one of these cases we're actually in will depend on how you proceed. So as we go through these, kind of pay attention to the type of information and how we'll go about figuring out what to do to actually get started and actually finish the solution of that triangle. Alright, so the first thing we're going to need to add to our list of things that we can use for the oblique triangles, beyond the only thing we know right now is that the sum of the three angles is 180 degrees, we're going to have to add some things before we can know what is useful in that category. So I'm going to go ahead and tell you what they're called. So to do these cases, we'll need to know the law of sines, which is what we're going to encounter today. and the law of cosines, which is in the next section. So beyond the sum of the angles being 180 degrees, these two laws will help us solve all triangles that we're presented with that can be solved. Okay, so those are the important things to know. So these are the bullet points for right triangles. This is the stuff that you can use. And for oblique triangles, these are the things you can use. And like I said, for the oblique triangles, it'll fall into one of 4 categories, 4 cases, and for each case there are certain things that you do to get started. And we'll talk about those as we go through these things. So first, what I'd like to do is to talk about the law of sines and figure out how that's done. So let's just say that we have some triangle. That's not supposed to be a right angle up there, by the way. Sorry, it kind of looks like it. Whenever I try to draw an oblique triangle, a lot of times it looks like a right one. So please just think about that as an acute triangle. That's what I was trying to draw. All 3 angles are supposed to be acute. So it's an acute triangle. And let's call this A and this B. Of course, these are arbitrary decisions. So which one's A, which one's B, which one's C? Because we have no hypotenuse, so there's no convention about how you name them. And for this triangle, I'm going to draw in the altitude, which is from any vertex, I happen to pick B, to the opposite side in a perpendicular fashion gives you the altitude of the triangle. The height of the triangle, if you want to call it that. Which is why we use letter H, by the way. Okay? And if we had done this same idea with an oblique triangle, I'm sorry, an obtuse triangle, like this one, where one of the angles is obtuse. Let's say this is A, this is B, and this is C. And if I want to draw the altitude from vertex B, it has to be perpendicular to the opposite side. So what that means is if I'm dropping this perpendicular to the line AC, I'm actually going to have to extend that line AC out, side of the triangle, and the altitude for the triangle can be, like in this case, exterior to the triangle. So, and what I'm about to say applies to both of these situations. In other words, it applies in all situations because every oblique triangle is one of these two. It's either acute or it's obtuse if it's not right. So, okay, now, if you were to think about the names of the sides of these, the convention is if this is angle A, opposite it is side A. So the whole base is side B, and this side is C. So this is A, and B, and C. And I'd like for you to look at, in both cases, and this will be true for both, which is good, I'd like for you to figure out for me, what is the sine of A? Well, I can't talk about sine of A unless it's a right triangle. Oh, wait, it is a right triangle. If you make the altitude H a side of a triangle and ignore the B, C, and base of that altitude, if you just kind of cover up the right side of that triangle, the left side of that, from A to B to the base of the altitude, is a right triangle. And so we can think about the sine of that angle A in terms of a right triangle, the one on the left, including the altitude as a side of the triangle, and that's going to be opposite H over hypotenuse C. Now find the sine of C. And by the way, if you look at the obtuse triangle, there's an exterior right triangle, and the sine of A is opposite H over hypotenuse C. Same thing. Okay, sine of C. So now you're looking at the right-hand triangle for the acute one. And the sine of C is opposite h over hypotenuse of that triangle is A. And for the obtuse one, that's the same thing. The right triangle there is a big triangle that goes from B to C to the base of the altitude. That's a great big triangle. And for C, H is opposite and A is its hypotenuse. And if I were to solve in each case for H, so in this case I'm going to multiply both sides by C. And in this case, to solve for H, I'm going to multiply both sides by A. And of course, the altitude is equal to itself. So by substitution, that means that C times sine of A is equal to A times sine of C. And that's the beginnings of the idea of the law of sines. If I were to divide both sides by sine of A and sine of C, on the left side, the sine of A's would cancel, leaving side C over the sine of angle C equals, and on the right side, the sine of C would cancel, leaving side A over the sine of A. And I could have picked the altitude to be from, say, vertex A or vertex C, and we would have gotten another version of the law of sines. And as it turns out, there are three versions of it. You could have A over sine of A equaling B over sine of B, or you could have B over sine of B is equal to C over sine of C. These are the three versions of it. And a lot of people will collapse this into one statement. But what this statement means is take any two of those at a time and they're equal. So basically one of these three that I've already written is what you'll use. But this is a nice compact way of writing the equality of all of these fractions, where we take a side divided by the sine of the opposite angle, and any two of these will be equal to each other, meaning any of those three statements joined by the conjunction are going to be usable as the law of sines. So this is the law of sines right here in abbreviated form. And what that abbreviated form means is take any two and set them equal to each other, and that equation will be valid. So those three equations I have up above it are all valid. Okay, so that's the law of sines. So let's get into solving a triangle. So the first example is solve triangle ABC if A. Please keep in mind that uppercase letters are always used here for angle measures. And like I said earlier, that'll be in degrees. Angle A is 32.0 degrees. Angle B is 81.8 degrees. And side A is 42.9 centimeters. One of the strategies I would like for you to employ, which will help you get your thinking straight as you do these problems, is try to sketch a graph. It doesn't have to be perfect by any means, but a lot of times you'll be able to see things better when you have a sketch of what you're dealing with. So I'm going to start by drawing what I think is about a 32-degree angle. The sketch isn't supposed to be perfect. It's just the idea of that's about the size of A. And I'm going to make B over here, and I need 81.8 degrees. Let's say that that's 81.8 degrees. Probably is not really. And of course, if it's triangle ABC, this third angle is is C. Sorry. So angle A is 32 degrees, angle B is 81.8 degrees. So we know this one. We know this one. C is unknown. And in fact, whenever I see that I have two given angles, the very first thing I would do is find angle C. Because the total of all three angles, 180 degrees, minus the measure of A and B, so subtract both of them, will give you the size of the remaining angle, in this case C. So what do you get for C in this case? 66.2 degrees. So we have one item that we found. We do have to know all three angles and all three sides. So right now we do know A, but we don't know B and we don't know C. Now, in order to use the law of sines, using one of those three equations up above where you can barely see all of them in compact form in the box, you have to know. Let me roll up to here. Let's look at the very first one. And let's just pretend like this is something we can work with. If A over sine of A equals B over sine of B. If there are four things in that equation, to be able to solve for one of them, you have to know the value of the other three. So you have to have three of those pieces of information known. So what I'm going to be saying in regards to this is you have to have a pair, a side angle opposite pair that you know. You either have to know side B and angle B, or side A and angle A, or even side C and angle C to make any headway here. The good news is in this problem, we can use the law of sines because we have angle A and its opposite side A known. That's the only way we could proceed with law of sines. Thank goodness we have that. So I know that A, which is 42.9 over the sine of A, which we know is 32.0 degrees, should be equal to, and now it's our choice. If we are finding B, we have to know angle B, which we do know. So let's go ahead and do that one. So that would be equal to B over the sine of angle B. So notice we knew three of the four pieces of information. Setting up this equation allows us to solve for the fourth one. The thing we're trying to find here is side B. So to get side B by itself, I'm going to multiply both sides of the equation by the sine of 81.8 degrees. And one of the things you'll notice that I almost always do is I rearrange the order of the equation to my desired order so that the variable I'm solving for is on the left side. It's just something I always do. So I switched the sides of the equation, and I also multiplied both sides of the equation by the sine of 81.8 degrees. So make sure your calculator is in degree mode, and I would like for you to type this calculator ready form of B and get an answer. So pause the recording and type this in and make sure you can get the correct answer. Okay, what you should have gotten for B is 80.128. That's using our rounding convention of three numbers after the decimal point. If we'd been using significant digits, the information has three, we would have made it 80.1. So please pay attention to any directions about rounding. 3 decimal places is what I want you to use, but if the problem says using significant figures, then make sure you do that. So read the directions, in other words. Now, are there any units on the length of a side here? Because that's what we found was the side B's length. Yeah, if A is in centimeters, B has to be in centimeters as well. So please don't forget to put units on your answers if there are units involved. There are some problems where the length of the side is not measured in any unit. It's just 42.9, nothing. So your answer would not have to have units in that case. Okay, so what's the only thing we don't know? Side C, right? So as I've said at least once before, as much as you can, try to use givens. So I'm going to reuse the law of sines with the A pair that I was given at the outset. This is the pair for which I have both given values. A and angle A are both known. And this time, I'm going to solve for C by using another version of the law of sines, which is C, which is unknown, over the sine of angle C, which is calculated, but since those weren't approximate, those were exactly 32.0 and 81.8 degrees, I know that C is actually exactly 66.2 degrees. So I don't feel like I'm using a rounded, not so perfect number. This is perfect. It's exactly 66.2 degrees. Okay, so the technique for solving here is like the other one we did. Basically, it's the law of sines twice. So I'm going to multiply both sides of the equation by the sine of 66.2 degrees. And it's now in calculator ready form. So type this in and see what you get. Notice I'm writing approximately equal to when I'm rounding. So C is approximately 74.071. Okay, am I done? Nope. What did I forget? Units. Yeah, I have to have units. So, what are the units of this? Centimeters. Very good. All right. So, let's turn to another example. So for this next application example, a surveyor wishes to measure the distance across a river, and they give you a picture of this, so that helps. She determines that C is 112.90 degrees, so that's given. A is 31.1 degrees, and that's given. And B is 347 feet. So this would be angle B over here, which means that B is this side that's given. Okay, so we have angle, side, angle. Find the distance A. So notice in this problem, we're not asked to solve the entire triangle, just the one side A, which is the distance across the river. So in order to do this, we're going to have a pair, a side and angle pair with the same name, both A, both B, or both C, to do this. Since side B is the only given, we have to know angle B, and luckily we can find it because we know the other two angles. So B is the sum of all three angles, 180, minus C, which is 112.90 degrees, minus the other given angle, which is 31.10 degrees. And so when you do that subtraction, you end up with B is equal to 36.00 degrees. Okay, now I have the pair angle B and side B, so I can set up A, which is what I don't know, over the sine of angle A, which is the 31.10 degree angle, equals B, which we were told was 347.6 feet, over the sine of angle B, which we just calculated, and it's 36 degrees. So to solve for A, multiply both sides by the sine of 31.10 degrees. And when you do that, you'll get this calculator ready form. And type that in your calculator and make sure that you get the answer 305.464. And should there be units here? Yes, feet. And that's the answer to the question. All right, so let's go to another example. So the next example is two stations are on an east-west line 110 miles apart. So here they are, 110 miles apart. A forest fire is located on a bearing of north 42 degrees east from the western station at A. So this is A. And let's draw the north line. Let's do north. And then our bearing is supposed to be from north. We're going to move 42 degrees in an easterly direction. So I don't know exactly what 42 degrees is, so I'm going to pretend like that's 42 degrees. Okay. There's a fire somewhere along this ray. Don't yet know where it is. And a bearing of north 15 degrees east. So from the eastern station at B. So this is the eastern station at B. And the bearing is north 15 degrees east. So let me see if I can draw that. Here's north. Actually, let me go back. I'm going to make that extend further, just in case we need it to be extended further. So there's north. There's north. Okay, so, and we're going 15 degrees east of north. Oh, well, this needs to be a pretty small angle for 15 degrees, and it's somewhere on that ray. Well, I didn't draw this ray long enough, so let's keep drawing it until they meet. Well, boy, did I underestimate the size I needed for that. Ooh, wow. Okay, so, and that's 15 degrees. Alrighty. So, how far is the fire from the western station? So the western station is A. From there to the fire, which is located right up here someplace, color that in red so it looks like a fire. And we're supposed to find that length of that green segment, which, since it's across from angle B, so if you ignore the north line there for a second, that angle B is in the triangle. And we need to call the side opposite it side B. So our task is to find B. That's the distance from the western station to the fire. Okay, so again, we only need one piece of information in the end. We don't have to solve the whole triangle. Okay, so how are we going to do this? Well, we don't have any of the angles labeled. We don't have any of the angles A, B, or C that are labeled. We don't have their values, so we're going to have to calculate them. So let's think about this a moment. If the north line at A and the AB line is east-west, then between the white and the blue is a 90-degree angle. And if from white to green is 42, how big is the angle at A? How big is this angle right here? Well, the right angle, 90 degrees, minus the 42 degrees from white to green leaves a 48-degree angle right there. So that's 48 degrees. Let's see, what else can we find? Oh, between the blue line and the other white north line, the one that goes up from B, we know that's a right angle. And so the angle B, which goes from the blue to the pink, is the 90 degrees from AB up to the north line plus 15 degrees to complete the angle. So that angle is 105 degrees. Now the only side that we were given is opposite C, so we're going to have to calculate C. And since we've now figured out what A and B are equal to, I think we can do that. The sum of the 3 will be 180 degrees minus the 48 degrees that A is minus the 105 degrees that B is, and C ends up being 27 degrees. So that's 27 degrees up here. Well, that's opposite the side 110 miles. So we have that pair that we can use to solve for the unknown B. So we know that side B over the sine of angle B. You know what? I did a lousy job of labeling stuff down here. This was angle B, and this one was angle A. I probably should have labeled that so it would have been easier to find what I wanted. And that may have been what messed me up just now. I wrote sine of B instead of the number that B is. So I apologize for that little faux pas. Getting back on track, B is the 105 degrees. And then the pair that we know is side C, which is 110 miles, over the sine of angle C, which is 27 degrees. So to solve for B, we're going to multiply both sides of the equation by the sine of 105 degrees, which puts this in calculator ready form. Type this in your calculator. Don't forget units. So how far is that? What do you get when you type that in? I get 234.040. And what are the units? Miles. All right. So, looking at the next slide, for any angle theta, sine of theta in a triangle, any angle theta, the sine of that acute or obtuse angle is between 0 and 1. If sine of theta is 1, then that means theta is 90 degrees, meaning you have a right triangle, and you can use all of the right triangle things that we talked about at the beginning of this lesson. Second thing, the sine of theta and the sine of its supplement are always the same. So the sine of theta and the sine of 180 degrees minus theta are going to have an equal value. 3. The smallest angle is opposite the shortest side, the largest angle is opposite the longest side, and that leaves the middle value angle is always opposite the intermediate side. And that's assuming that you have 3 different lengths. If it's a isosceles or a equilateral triangle, then some of that isn't true. But this is assuming all 3 are different. The bigger the angle, the bigger the opposite side will be. Okay, now let's start talking a little bit about what we might encounter. First, let's say that we have an acute angle that's given. And the information they give us is side-side angle. So the given angle A in the side-side angle, that angle is acute. And so this is that one that makes sophomores titter and giggle, is if you write it backwards, it's the word ass. And so you might remember this is the one that's the most complicated of them all. So let's assume that angle A is acute, and we'll talk about when it's obtuse that's given in just a minute. So that's kind of a different case. I always draw the angle side-side, or side-side angle, in a certain way so as to be able to rely on the way the picture looks to inform what I'm doing. So I always put the given angle at the left-hand side like that. And if it's side-side angle, I'm going to assume that one of the sides that's given is this one. That's my first side. And the second one that's given is this one. And the angle that's given is that one. Okay? So that's side-side angle. And a lot of times I'll draw the green one too short to remind me that there might not even be a triangle. Now, one thing about this is this angle up here is not fixed. It's like this side can swing wherever you want to swing it, and it won't change its length. And the goal is, if you're going to form a triangle, it has to hit this side down here. And the way I've drawn it, it's obviously too short. When you swing it around, it's never going to touch that third side, which is a no triangle situation. Okay, let me tell you what else is behind this one. For a while, we're going to be talking about the case where, let's see, wait a minute. This side over here would be called side A because it's opposite angle A. And let's just, for the purposes of argument, let's say that this side that's given is called B. It could be C, but let's just call it B for having something to talk about. Well, one of the things that is putting us into this situation is that we have A shorter than B. Okay, so it's going to be a different situation if A is longer than B. And we'll talk about that in just a minute. We'll get through all of the possibilities. So for right now, let's, besides having an acute angle that's given, the two sides that are given, the side opposite that acute angle is shorter than the other side given. So these are kind of the two guiding principles for this. Now, in order to come up with the idea that there is no triangle, it's no triangle because that side never hits the angle, the side A never hits the bottom of that triangle, but well, potentially a triangle. Let me call this, so that's side B, angle B would be over here, right? So this would be angle C. So this would be side C. So if side A is too short to touch side C, we have no triangle. And what do I mean by too short? Well, the closest that swing gets to side C, the very closest it can get is at a right angle. So what I'm going to do is I'm going to draw in that altitude of the triangle. And we'll be able to tell that we have no triangle when the acute angle and A smaller than B is given. If A is too short, it means it's shorter than the altitude of the triangle. So we'll have no triangle if A is less than H. Well, now we have to figure out how do we know what H is? Because all we'll be given is side A, side B, and angle A. Well, if you notice, the drawing in of the altitude created a right triangle. AC, base of the altitude. That's a right triangle. And how would angle A that's given and side B, which is part of that triangle, the hypotenuse in fact, be related to side H, the leg of the triangle opposite A? Well, of course, it is true that the sine of A, since it's a right triangle, will be opposite, which is H, over hypotenuse, which is B. So if I solve that equation for H, I'll multiply both sides by B, and the altitude will always be, because it's not always called A and B and C, it will be one of the sides that's given times the sine of the angle that's given, and the angle name A can't match the side. So it's not A sine A. If you're given angle A, you have to use the other side that doesn't have the same name as A, and the altitude will be that other side times the sine of the given angle. And so that's how you'll find the altitude. So that's going to be a calculation I require that you do in the side-side angle situation, is you're going to need to, for acute angles and A less than B, you're going to have to find the altitude. That's just part of it. So kind of make that something that you know how to do. Okay? That's important. Okay, well, let's talk about another case. What if we're given the same kind of information? This is angle A. This is side B. This is side A. And keep in mind that angle C is not fixed. It is not given. So it can move. This is not a fixed thing, so it can move. And that can swing this way, which isn't helpful, or this way. And, oops, I didn't draw that quite right. It's actually a pretty good pun, as you'll see in a second. It swings like this and hits that side that's called C in exactly one place. And in fact, the one place it hits is when the length A is perfectly the same length as H. So if A and H are the same, then that means that you're going to have one right triangle. And you'll need to solve that triangle. And we're going to talk about some examples here in a few minutes of all of these. So right now I'm just talking through the possibilities. But I want you to kind of see what the possibilities are before we get into examples. Okay, then the third possibility, given angle A, side B, and side A, where again A is acute, and it's a given angle and it's acute, And side A is shorter than B. That's true in all of these three examples I've drawn so far. And this time, when you swing side A, that's shorter than B, if you swing it, it actually hits right there once, and you keep going, and it hits it again over here. And so there are two places where you can draw A, the side A. You can draw it to the first orange dot to the right, or to the dot that's a lot closer to A, and that will create two different triangles. And they will be oblique, meaning not right. And how will we know that that's the case? Well, we've been comparing to the altitude, so let me draw that in. And at the point when you swing that through the altitude location, isn't it a lot longer, because it's down here below the line? It's a lot longer than the altitude. So that's the situation. If A is greater than H, you have two oblique triangles. Okay? So those are the possibilities if you have an acute angle given, side A that's given, which is the same name as the angle that's given, is shorter than the other given side. A is less than B in my pictures. And comparing the value of A to the altitude of the triangle, which you find by multiplying the other given side, not A, but the other one, B, times the sine of the given angle, that'll give you H. When you compare A to H, A has to be smaller than H, equal to H, or greater than H. One of those three things has to be true. And that will lead you to no triangle, one triangle, or two oblique triangles. So that's that situation. Okay. So let's talk about same beginning idea, acute angle given. But this time, let's talk about what if A is longer than B. So I'm still keeping the acute angle. Let me just write that again so that it's really clear. It's still an acute angle given. But this time, let's let A be greater than B. And let's draw that picture and see what happens there. Okay, so angle A is acute, it's given. Side B is given. Length A is given, and it's longer than B. Now, by the way, this space at the bottom, you'll sometimes draw it too long at the outset or too short, and so don't feel bad about going back. That side can be any length it needs to be to form a triangle. Okay, so I'm just going to extend that out. And if I were to swing this down, because remember, side A can be swung through because it's not a fixed angle. It can be swung to wherever we need it to be to form a triangle. And if we swing this, it's going to swing down and hit right there and form a triangle. And if you swing this way, keep going this way, it'll never hit that side again. So that's the only triangle that you'll get. Just one triangle. And that's not something that's in doubt. It's not ambiguous at all. If A is greater than B, you definitely have one triangle, and you just need to solve it. Okay? All right. So now let's talk about if the given angle is obtuse. Obtuse angle given. So this was still acute angle, and A greater than B there. This is obtuse angle. And let's see what our possibilities are there. So we have an acute I'm sorry, an obtuse angle, let's say it looks like that angle A is given. Side B will be given, and side A will be given. Let's say it's that long, right there. Well, if you, again, angle C is changeable to whatever you want it to be to make a triangle, which means we can swing this through, and the only way we'll get a triangle is if side A hits this side over here, and it never will. And why can we say that? How do we know that that's not going to happen? Well, we'll get no triangle in this case because A, whoa, sorry, that looked bad. That L just kind of escaped me there. It didn't look very good. So there'll be no triangle if A is shorter than B. Does that make sense? It's too short to hit the side where the question mark is, side C. So we'll label that side C. So no triangle possible. What if A is exactly the same length as B? Well, it's going to swing and hit right at angle A, and A and B sides will be lined up on top of each other. That's not a triangle, that's two segments that are the same length on top of each other. So there'll be no triangle if A is equal to B. There'll be no triangle if A is less than B. All right, now let's talk about another situation. Same idea. Oops, well, that didn't look straight, but that's okay. We'll go with it. Angle A would be given, side B would be given, side A would be given, and let's assume A is longer, because that's the only other possibility, than B. If A is longer than B. What's going to happen when you swing this around? Oops. Well, that was not very well drawn. Let me try that again. So if I swing this around, it hits right there and never again. So it's going to form exactly one triangle. So of all of these situations where it's side-side angle, or angle side-side if you prefer, there are a lot of possibilities, but if you draw the picture and you can say, oh, look at that, it's obtuse, and A is too short, no triangle, duh. Or A is longer than B, so yeah, there's a triangle. So the pictures really help, and most of them are not ambiguous. These last ones we've done, it's either one or no triangle, and there's no other possibility. It's the first three that cause us the most difficulty. Okay, so that's when you have to compare A to the altitude, and it's either too short or too long or just right, which gives you a right triangle, by the way, if it's just right, exactly the same as the altitude. So that means that we have pictures to help us make decisions about what will work and what won't, if we'll even have a triangle to deal with in the problem. Okay, so what I'd like to do now is to do some more examples. Go up here and get some blank space. There we go. And let's do some examples where we have to figure out what's going on with each triangle and probably draw a picture to help. So let's do this example. Solve the triangle ABC if angle B is 55 degrees 40 minutes. Okay, already they haven't stayed with our convention of A will be the one given. So I want you to realize you need to think about the relationships amongst the sides and angles that we talked about, and not so much get hooked on it has to be this letter, because many times the letters are not A, B, and C, or they've used B as the angle, whereas we thought of it as A. You're going to have to make that kind of transition easily. So it's kind of like the Pythagorean theorem. Memorizing a squared plus b squared equals c squared is not as useful to me as thinking leg squared plus leg squared equals hypotenuse squared. It's really a better situation to have the relationship than be tied to. It has to be these letters, okay? Because that's going to really mess you up. All right, so this is the given information. B is 55 degrees, 40 minutes. Side B is 8.94 meters, and side A is 25.1 meters. So let's just draw it. 55 degrees, 40 minutes is about like that. Probably not to scale, and that doesn't matter to me as much that it be perfect. It just has to be definitely acute. So that's what I was going for here, was an acute angle, less than 90 degrees. Side A, I'm going to label right here, and it's 25.1 meters, of course. And that means that side B, which is always across from angle B, that's given to be 8.94. And that is shorter than 25.1. So I'm going to draw it shorter. And this is that ambiguous case where it may be so short that there's no triangle. It might be just the right length so that there's one triangle that's a right triangle, or it may be long enough to give us two oblique triangles. So I draw it too short on purpose. So that reminds me, since it's shorter than A, that I need to think about the ambiguous case, which means I need to figure out what H is. So H is going to be something sine something. The angle that I'm going to use is the only angle given. And the side that I use doesn't have the same name as that angle. So that angle is called B. So what goes in front of sine is A. They have to have different names. In the formula, it was A sine B. B sine A. And this is A sine B. So you can't get too tied to the actual name of the letters. So type that in your calculator and figure out what that is. You should have gotten 20.7268. If you're having trouble typing in that angle, you might want to ask about that in class again. That's something we talked about earlier. But if you've forgotten, please do ask about it. And by the way, in your notes, as you're taking notes, in listening to the lectures, you might want to give some kind of signal to yourself, hey, I need to ask about this, or I don't know how to do this pre-calculus thing, or I don't know how to do this calculator thing, so that when we're in class, you can ask me about those very specific things, and I can help you with what you're needing help with. Okay, so if you look at the picture, B is 8.94, which is a lot shorter than 20.72, so it is definitely too short to cause us to get any triangles. It'll swing like this and not hit the opposite side down there at the bottom, side C. And so no triangle. So what's our justification? Because B is shorter than the altitude. So we would say since B is shorter than the altitude, there's no triangle. And I'm not saying that it's necessarily going to be called B. This is for this problem. Since the B that we were given is shorter than the altitude, there's no triangle. And actually, that's kind of cool. It's a very short problem and very easy to do. Okay, let's do another example. Let's say A is this time 55.3 degrees. I don't know why I got stuck on the 55 degree something angles. Just doesn't matter. And side A is 22.8 feet. And side B is 24.9 feet. Okay, so let's draw a picture of that. Angle A is about 55 degrees, give or take. Side B is given, and it's going to be 24.9 feet. And side A is shorter than it. So let me make this a little bit longer. And side A is shorter than that. And again, I always draw this too short on purpose because I don't know. Is it going to be too short, just right, or long enough for 2? So, to make that determination, we need to compare A to the altitude. So, the altitude is going to be B, 24.9. Sine A, notice those have different names, B and then A for the angle. And then tell me what you get there. I got 20.471. Okay. So, this time, H and A are not the same, so it's not a right triangle. This time, side A is longer than H, and that implies 2 triangles. And that means we get to find both of them. Especially in the 2 triangle situation, we're going to be needing to store numbers in our calculators for use in later parts of the problem. So make sure that you know how to store numbers for later use in your calculator so that you don't have to retype a rounded version of that number. You can pull back all of the digits the calculator has in it for that number. Okay. So now we know there are 2 triangles. Let's get going. The 2 triangles that we'll get, let me draw B just a little bit longer so that I realize I'm going to get 2. The first one is when I swing through and hit there. The second one will be when I swing through and get in over here. So I'm going to draw these 2 separate ones apart from the other stuff I've drawn so that it's easier to sort of understand than you know, the mixed up drawing that's up there that has all the possibilities. So this is the first one. This is your 22.8, which is side A. This is angle A, which we have given as 55.3 degrees. So that's given, and B is 24.9. Okay, so this must therefore be called angle B, and this is therefore angle C, and this is side C. All right, here we go. Now, since it's not a right triangle, we have to hope either that we have 2 angles and we can find the third, which is not the case here, or we're going to have a pair that are known, either A and A, angle A and side A, or angle B and side B, or angle C and side C. One of those pairs has to be known. And the good news is A is known for both. Okay? Now, one of the things I want to say about the law of sines really quickly, because this is a nice thing to know. Before, when we wrote it, we wrote the side over the sine of the angle, right? And this is just one example of the three that are possible. And that's really handy when what you're solving for is a side. Because it's in the numerator, all you have to do is multiply both sides by sine of b to find side b. But a better version is available to us if we took that equation and took the reciprocal of both sides. So sine of a over side a equals sine of b over side b. This is an alternative form of the law of sines, and it's particularly useful when you're solving for an angle. It's in the numerator. So to get angle b, you'd multiply both sides by b and then use sine inverse to calculate angle b. So because we are given sides and we don't know angle b in this case, that's the version of it I want to use. Okay? So the pair that I have is a. So sine of a, 55.3 degrees, over side a, 22.8 feet, should be equal to the sine of b over the length of b, which is 24.9. So notice again, of those four items, I have to know three of them to find the third. I have to know three of them to find the fourth. Wow. Okay, so I'm going to multiply both sides by 24.9. And that will give me 24.9 sine of 55.3 degrees divided by 22.8. And then to find b, I'll need to use sine inverse of that mess. This is now in calculator ready form. Once I finish writing it. So type that in your calculator. And this is the first time we've had that type of thing to type, so I'd like for you to pause the recording and make sure you get the right answer. So type that in. Okay, so you should have gotten 63.879 when you round to the third number after the decimal. 63.879 degrees. Store that number in your calculator because you're going to need it again. In fact, every time you get an answer in the side-side angle problem, especially if there are two triangles, you need to start storing stuff in your calculator. Otherwise, you're going to be doing a lot of retyping, which is really annoying. So I'm going to write store, and you might write that, but depending on how your calculator memory works, if it calls it a letter, I would store it in B because it's not that hard to remember. If it's a numbered storing system, I would put A in 1, B in 2. Or, you can do whatever you want. Just remember where it is, but store it someplace, and then you'll have it. All right. So now I know angle A and angle B, so I can find angle C because I know the sum of the three angles is 180. So C will be the total 180 degrees minus the size of angle A minus, and if that's still in your calculator, a lot of you can bring that back with answer A and S if you know how to do that. Otherwise, recall it. Do 180 minus 55.3 minus, and then recall that number and pull it back in, and that'll give you angle C. Okay, and angle C therefore is 60.821 degrees. Oh, and I forgot, they have a convention here that I think is probably pretty good. We're always going to find this triangle first because it's the easiest one. It's like you're swinging, go back up here to the top picture, you're swinging that across. The first one you get to will be the first one you should deal with, and then do the one that stops over here second. I promise you it's way easier if you do it that way. So this will be an acute triangle every time when you do that correctly. So this angle C is our acute triangle C. Well, what we're going to do for this is, for our unknowns, I would like for you to adopt a system of calling this angle C sub 1, side C sub 1, and angle B sub 1. So I'm going to go back and call that B sub 1 all the way through. And this will be C sub 1. So that'll be C for the first triangle. Okay. Now notice the A that's given and the B that's given and the angle A that's given. I'm just going to call them by the regular letter because they're not changing. Between the two triangles, they're the same. Okay. So the only thing left to find is side C sub 1. What can we use to find that? Well, can't we use the law of sines again? Right? Can't we? So won't side C1 over the sine of angle C1, which we just calculated, which means we're going to need that number again. I probably should have told you a second ago to make sure you store that number. It should still be the last thing you typed in your calculator. We haven't done anything else yet. So before you do anything else, store this into C, or wherever you want to store it, whatever name you use for that. And then the pair that we know that was given was the A stuff. So that's going to be side A, 22.8, over the sine of A, sine of 55.3 degrees. So notice I'm in one case using the same old law of sines, side over sine of angle, whereas when I was finding angle B1 over here, I used the reciprocal. So I'm going to freely move between the two and use whichever one is the better for that particular problem. Okay, so I'm multiplying both sides of the equation by the sine of 60.821, which I am not going to type back in my calculator. I'm going to pull up the stored value for that when I do the calculation in my calculator. Anything that you've rounded, you don't want to type back in. You want to reuse a stored value. Okay, so C1 is approximately, let's see where I found that, 24.213. And what are the units for length? Do we know those? Yeah, they were feet. Okay, that's one triangle, the first of two. So now we've got to do number two. Alrighty, so let's draw number two. Angle A is still the 55.3 degrees or whatever, and that's given, so we know that. Side B is given, 24.9. And side A is given. Now you have to swing over. Look up at the top picture. You can barely see the bottom of that. That other one is going to be when you swing it way over here. Okay? And that's where A is 22.8. And notice that side at the bottom is too long. That's okay. If you want to erase it because it offends you, you can. But I'm not worried about that extra tail out there that we're not using. It's not that big of a consequence. So we're going to have to find C2. And look at the two triangles. Isn't C2 considerably smaller than C1, just the look of it, because of where side A ended up being? And this angle right here will be called B sub 2. And this short little bitty side over here will be called little c sub 2. And those are the three things we have to find in this problem. Okay? So, how are we going to find all of that? Well, I'm going to go back to my first picture and probably amend it a little bit. Let me draw that again. I'm trying to decide where I want to draw it. I think I'll draw it over here. Maybe I can make it fit right here, up here to the right. If this is what I'm getting in a sort of a general sense, that I get one here and one here. That's the two positions that A will take in this drawing, or in this situation. They're both A long, so they're equal to each other in length. And if you look at this as, ignore the blue stuff over to the left, but the blue down here, if you think about this part of that blue at the bottom, that forms a triangle that's special. It's isosceles. Do you remember that name? Isosceles. And in an isosceles triangle, the angles opposite the equal sides are in turn equal. So whatever this angle is, which by the way, that's B1, is equal to the angle over there. Now the question is, do you realize that angle B2 is this one inside of that little triangle over to the left? That angle that I've just drawn is B2. How is it related to B1? Well, because the side at the bottom is a line, B1 and B2 are supplementary. So in this type of problem, this is something you can say will always be true. It won't be the name B necessarily, but that angle in the bottom right, for what we're calling B, and the other angle B for the other triangle, are always supplementary. And that means that B1, oh, I'm sorry, I should have written B2, because that's the one we're finding. Oh, rats. Well, I made a mess of that. Let me just kind of start over. That means that when we're solving for B2, we're going to find it by subtracting B1 from 180 degrees, because they're supplementary. So good thing is we stored angle B1 a little while ago in our calculator, and this is where we're going to need it again. So that means that B2 is 180 degrees minus B1. So you're going to use the stored value that you got in your calculator. You're not going to retype 63.879 because you're losing some accuracy. Some of the digits behind this that you're dropping off are not being accounted for unless you've stored it in your calculator. So make sure you do. Okay, so that should be 116.1 degrees. 116 point, well, it rounds to that. 121 is what I want to say. Sorry. 116.121 degrees is what you should get. All right. So that's B2, and that's now done. Now that we know B2, we should be able to find C2, right? So what is C2? Well, if we know A and B2 already, the sum of the three angles has to be 180, so C2 will be the total of all three, 180, minus angle A, which is 55.3 degrees. Oh, and I probably should have told you, you're going to need this number again, so store it into B. And that's okay, you don't need that original B1 number anymore. So when you store this, you can store it back over into the same location of memory in your calculator, and it'll just overwrite it. So now if you pulled up B, it would pull up the 116.121. Okay, etc. I mean, pull up all the digits. Minus your stored value of B. And so if you type that in your calculator, making sure you use the stored number and not retype 116.121, angle C should be 8.579 degrees. A really small angle. And that sort of makes sense. Look at the picture. I didn't draw it to scale, but that being an 8.5 degree angle sort of does make sense because it will be kind of small. So the only thing left to find is side C2, and you can look above and see the procedure that we'll use is the law of sines again. C2 over the sine of angle C2, and I probably should have said as soon as you get each value you should store it because you're going to need it again probably. So you would want to have stored this one, and I would store it into C, and it will overwrite the old C, and that's perfectly fine because we don't need it anymore. And that should equal side A over the sine of A. Notice I'm using the givens, and I'm not using angle B2, which we calculated. You want to use givens as much as you can. So although I know the B pair, side B and angle B, I don't want to use that for the law of sines unless I can't do it otherwise. And I do have an option to use givens, so that's what I want to do. So to solve for C2, I'm going to multiply both sides by the sine of 8.579 degrees, which I'm not going to type that, I'm going to pull it up from memory, divided by the sine of 55.3 degrees, and so C2 comes out to be approximately 4.137, and what are its units? Feet, right? And we've solved both triangles. We're done with that problem. This is the problem you hope you don't have on the test, 16 or 17 of them. No, I would not do that to you. Please don't panic. You probably would have one, maybe two of these where you had two triangles and had to solve for both. That's too long of a problem to make. You do a lot of them on the test. They're the hardest, and they certainly take the longest of all that we've talked about. Okay. So there's kind of a number of triangles satisfying the ambiguous case, the side-side angle, which we might call angle side-side, the one that makes an ass out of you sometimes. It's just a summary of things that we've already talked about, so you can read through those and double check that you understand all of them. But really, I think if you draw a picture, you're actually in a lot better situation than anything else you could do. Okay? And it kind of tells you how to go about doing it. But if you draw a picture and think through, what do I know, what can I use? To use the law of sines, you have to have a pair with the same name, side and angle. The three angles add up to 180 degrees, and we have the law of sines. Those are your tools. And then when you draw the picture, that'll help you determine, especially in the side-side angle situation, is it 0, 1, or 2 triangles? That's something you'll have to determine as you go. All right, so let's do another one. Angle A is 43.5 degrees. Then side A is given, and it is 10.7 inches. And then side C is 7.2 inches. Okay, 43.5 is an acute angle. Looks about like that. Does not have to be drawn to scale, just got to look acute. Side C is 7.2 inches. And side A is 10.7. That's longer than C. And when that's the case, of course the side at the bottom can be as long as needed. If that's the case, then there's only one triangle possible. This is one of those cases we talked about. If it's an acute angle and A is longer than C in this picture, there's only one triangle. So all we have to do is solve it. So make sure you label things correctly. Since that's side C, this has to be angle C. So this would be angle B, and this will be side B. Okay. So knowing the A pair, I can find C, right? Everybody agree? Because I know side C. So I can find angle C using the law of sines. The sine of the unknown angle C over side C, 7.2, is equal to the sine of A, which we do know is 43.5 degrees, divided by the length of A, which is 10.7 inches. So first I would solve for the trig function, solve for sine of C by multiplying both sides by 7.2. And then use inverse sine to find angle C. Something I haven't mentioned yet because it hasn't become an issue on any of these problems, and it still hasn't, but it occurred to me that you need to realize that the law of sines can only be used in certain situations. And know that you're getting the right answer. Let me talk about that before I go any further. If you'll recall, inverse sine is an inverse trig function that only gives answers between negative pi over 2 and pi over 2. Well, since this is triangles, that'll be between negative 90 degrees, which doesn't make sense, to 90 degrees. And of course, the only things that would make sense in reality are the first quadrant answers for triangle problems. So, if I have an obtuse angle, would I ever want to use the law of sines to find it? The answer is no, because sine inverse will not give you an obtuse answer. It can't. So, you would never use the law of sines to find an obtuse angle. Just kind of keep that in mind as we're going. Now you might notice in the picture I've drawn, C is obviously smaller because 7.2 is smaller than 10.7. That means that angle C is smaller than angle A. And since A is 43.5 degrees, C has to be smaller than that, which means it's acute, not obtuse, and I don't have to worry about it. I just want to mention that so that in the next section, you'll not accidentally use the law of sines when you should have used something else, which is the next thing we're going to talk about in the next section. All right, so anyway, you should have gotten that C is 27.593 degrees. Okay. Now, what can we find next? Because C is done. Well, since we now know two of the angles, the best thing to do next would be to find angle B, the third angle. So we'll take the sum of all three, 180 degrees, and subtract the two known angles from that. Oh, I forgot again. I probably should have said store this number. You might need it again. Wish I could remember to say that. But luckily you haven't typed anything, I hope, since that. You've just been following along and thinking about what you're about to do and writing this stuff down. It's kind of what I'm thinking. That's what I'm doing. And I just now realized I'm going to have to subtract that number, and I don't want to type 27.593. I want to use that stored value. So that will give us a value of B, angle B, which is 108.907. And just to say, if you tried to use the law of sines to find angle B, if you could, you can't in this problem because you don't know side B. But if you were to try to do it, law of sines would not have worked. You would not have gotten 108 degrees because the biggest that sine inverse will give you is 90 degrees. So kind of keep that in mind. That's kind of important, and it will definitely play a role in the next section. Okay. So the only thing left is side B, and I'm going to use the law of sines. Side B over the sine of... Now you may be thinking, wait, you just said you can't use law of sines with that angle. Well, what I meant was you can't solve for the angle with the law of sines, but you can use the law of sines if you know the angle, even if it's an obtuse angle. So we're not finding an angle that's obtuse, we're using an angle that's obtuse, and that's a very different thing. Now, of the two possibilities, use the A's or use the C's, which one was given? Because that's what we need to use. Well, the A's were given, so we should use 10.7 for A divided by the sine of angle A, which is 43.5 degrees. So solving for B, we'll multiply both sides by the sine of that obtuse number. Oh, I forgot to say to store that one as well. Darn. Maybe you'll remember it and you'll be shouting at this thing. You're supposed to write store. You're supposed to write store. Don't forget to write store. It's not until I'm about to pick up my calculator that I think about, ooh, that number needs to be stored. And luckily, I haven't typed anything in the calculator, so it's still sitting right there. I just have to do the storing process right then before I type anything else in the calculator. Otherwise, I'll have to go back and retype what gave me that number, which is kind of a pain in the rear. Just saying. Okay, so when you find side B, you should get 14.706. Does that have units? Yeah, it's inches. All right. The next thing is sort of just a common sense question. I think if you think about it, it'll make a lot of sense. So it says, without using law of sines, we're not really supposed to calculate something. We are supposed to be able to explain why if angle A is 104 degrees, and that's not exactly 104, but you get the idea. It's bigger than 90. It's obtuse. If that's 104 degrees, and that's why drawing a picture is so helpful, and side A is 26.8, so this over here is 26.8, and I don't know if I'm going to make a triangle or not yet, so I'm going to draw it too short just in case. Meters, 26.8 meters. And B is 31.3 meters. that cannot be a valid triangle. Well, that's just one of our situations. Let me erase some of that because I actually made side A long enough to look like it would actually touch. It's actually way shorter than, well, let me just redraw that degree symbol. Maybe exaggerating it a little bit there, but it's definitely shorter than the 31.3. So let me erase some more of it. And from the picture itself, you can say, well, gee, it's that situation I described. So you would say, since A is obtuse, and side A is shorter than side B, that's enough. There can be no triangle. That's a description of what makes it not a triangle. And the picture, I think, really helps you see that, especially if you try to sort of draw it to scale. Like I exaggerated the shortness of the 26.8 compared to the 31.3. Makes it a lot clearer that that's too short, and if you were to swing it along, it would not hit the bottom line, the side C, I guess that would be. So it's too short. Okay. So that's an attempt at a piece of logic, basically. Can you figure the logic of that? All right, so that ends this lesson. I will see you in class.